لقد قام باختراع شيء كهذا يسمى ميزان الالتواء. يشتمل على 4 أجسام كروية صنعت من الرصاص، كرتان منها ثقيلتان وكبيرتا الحجم، وقد ثبتتا في مكان معين، ويتدلى منهما سلك دقيق وهو قضيب خشبي يبلغ طوله 6 أقدام، وقد علقت على طرفيه كرتان صغيرتان. العلاقة بين الكرة الكبيرة والصغيرة هي أساس الاختبار. ثمة قوة جذب تسحب الكرتين إلى أسفل بسبب الجاذبية الأرضية، ولكن يرى نيوتن أنه لابد من أن تكون قوة الجذب التي تشد إلى أسفل بين الكرتين ضعيفة، وهذا ما كان كافنديش يحاول قياسه. يجب أن تحدث أي حركة خفيفة من الكرة الصغيرة باتجاه الكرة الكبيرة انحرافا في سلك الالتواء، وهذا ما كان كافنديش يحاول اكتشافه. الكلام عما سبق أسهل بكثير من القيام به بالطبع. كان هذا الاختبار شديد الحساسية، فقد يؤثر أبسط اهتزاز أو أخف نسمة أو أي تغير في درجات الحرارة على القياسات. لذا اضطر كافنديش أن يضع الجهاز داخل صندوق، ويضع هذا الصندوق داخل كوخ، حتى إنه لاحظ أن مجرد وجوده قرب الجهاز قد يؤثر في فعاليته، لذا كان يضطر إلى الخروج بسرعة من الكوخ. ما فعله لاحقا هو أنه كان يجلس خارج الكوخ ويحدث ثقبا صغيرا في سقفه، وينظر من خلال التلسكوب ليلاحظ أبسط انحراف في الأسلاك. لقد كانت عملية شديدة الصعوبة، ولكن بعد أشهر شعر بالثقة الكافية التي مكنته من التوصل إلى نتيجة. اكتشف كافنديش أن الكرات الصغيرة تحركت مسافة يسيرة تبلغ 4 مليمترات. لقد قام بحساب نتائجه عن طريق إجراء مقارنة بين كثافة الكرات وكثافة المياه. في النهاية أوصلتنا نتائج اختبار كافنديش وحساباته اللاحقة إلى أن كثافة الأرض كانت تبلغ 5 أضعاف ونصف كثافة المياه. بطريقة أخرى، بلغت كتلة الأرض 5.9 تريليون كيلوغرام. والجدير ذكره أن كافنديش حصل على هذا الرقم بهامش دقة يبلغ 1%. بفضل نتائج كافنديش المذهلة، تمكن العلماء من التوصل إلى قيمة الجي، ويمكن استخدام المعادلة لتحديد كتلة أي جسم سماوي يدور حول جسم آخر. إذن تمكن علماء الفلك من حساب كتلة الشمس والكواكب والقمر، حتى إنهم تمكنوا أخيرا من حساب كتلة المجرات البعيدة.
Have a look at Cavendish's apparatus. It consists of 2 pairs of spheres. One, a small pair of spheres, and the next is a large pair of metallic spheres. Now let us try to understand how this instrument helps measure the universal gravitational constant, G. Basically, the smaller pair of spheres is attached to either side of a light wooden rod, suspended from a rigid support by quartz fiber, and is free to rotate by twisting the fiber. The setup is kept within a closed environment to avoid air currents. The other 2 larger metallic spheres are brought from a distance close to the smaller spheres. They are placed at an equal distance on either side of the small spheres so that all the 4 spheres lie in concentric circles. The gravitational force of attraction between the smaller and the bigger spheres causes the smaller ones to move towards the larger ones. Hence, they move along the arc of a circle with a radius equal to half the length of the rod. The system of horizontal rods rotates till the torque due to gravitational force between the spheres.
We've moved over into a garage to get away from the hustle and bustle of the studio. We're going to repeat an experiment performed by Cavendish more than 100 years ago. We're going to try to measure the force of gravity between a box of sand and a bottle of water. You could repeat this experiment yourself if you wanted to. It's not too difficult. But instead of using just one bottle, we have 2 bottles of water and 2 boxes of sand. Now, 2 bottles of water are suspended from a yardstick that you can see. The yardstick, in turn, is suspended by means of some recording tape, thin recording tape, that goes clear to the ceiling. The period of oscillation of this torsion pendulum is pretty slow, about 10 minutes. So what we're going to do is to show you the oscillation of it in stop frame photography at a rate of about 60 times normal. In order to show the angle of twist of the pendulum, we have a mirror attached to it right down here. A light spot is reflected from it, shows it swing on the wall. The period of the pendulum is really 12 minutes, but you see it here in 12 seconds, as the minute hand of that clock shows. And I'll mark the middle of the swing, like that. Now we're ready to put the boxes of sand in place so that they can pull on the bottles. Okay, now we're ready to watch the sand pull on the bottles. It's swinging. And the center of swings is displaced over to one side. And I'll mark a new center of swings. Now, instead of setting the boxes back the way they were originally, what I'll do is to move them around so that they deflect the pendulum in the opposite direction. This will give me twice as big an effect. There it goes. Now it swings over to the other side. And there you've seen the effect of the force of gravity acting between relatively small bodies. Question is this a powerful force? You know that it doesn't take much to twist a piece of recorder tape, especially if it goes all the way from the floor to the ceiling. But it's common to think of gravity as a large force. But you remember that the mass of the Earth that pulls on you is a lot bigger than the mass of that box of sand. Notice another thing. Notice, too, that the glass and the screen wire had no effect. But the screen wire is there for a reason. Watch this experiment. I can charge this lucite rod up here by rubbing it on my sleeve and pick up a piece of paper very easily. Let's see if that charge, which you proved to be there, see whether that has any effect. None at all. The screen wire shields it out. But let's see what happens now if I very gently lower the case and hold up this charged rod. Practically jumps out of the case. Look at that. The electric force is tremendous compared with the gravitational force. We'd better go back to the studio and look at that electrical force a little bit more. You just saw this electrified rod pull on a bottle of water, just as it does on this ping pong ball. But there's one big difference. I can rub this off. And you can't do that with gravity. Well, one more thing. The force depends on the distance. Watch. Closer I get, the harder it pulls. And one more. Suppose I let it touch. Then it'll repel. And you never saw gravity repel.
Okay, we're going to be trying out the Cavendish experiment here. I've been letting the torsion balance come to rest over the course of about 24 hours now. Even with that amount of time, I think just from the air circulation, from the heating and cooling system, I've still seen a small amount of motion here. So in the last about 10 minutes, I've seen this end move from here over to here. So that's probably about 10 degrees in 10 minutes. I'm going to let this, I'm going to just gently touch this and try and bring it to rest and observe for another couple minutes. And then whichever direction I see it moving, I'm going to put the bowling balls that are my other masses on the opposite side as that, just so we can verify that there actually is a change in direction, a change in the direction of the acceleration of these things as they rotate. I don't think we're going to be able to get it to a position where they're totally stopped initially. So this seems like the best way that we can still verify that there is some force from gravity between the masses I have on the ends of this meter stick and the bowling balls that I'm going to put in place. So very gently, I'm going to be just trying to stop any motion that we have in there, just a tiny, tiny force. I'll mark where it is right now. Whichever direction I see it move in. After this, I'm going to put the bowling balls on the other side. No, actually, I'm going to try this again. I think I gave it a little bit too much force, even with just that very gentle touch. I see it already moving quite a bit. Let's check that one more time. Okay, looks like that's moving just very slightly, if at all, right now. I can't see any motion. So we'll let that go for a minute, see which direction it's moving, and then put the bowling balls on the opposite side. It looks like in the time that we've let it go, it's moved from here over this way, so it's rotating counterclockwise when viewed from above. So I'm going to put the bowling balls in place on this side and that side over there, try and pull it back clockwise, and we'll see if we can get some noticeable acceleration in that direction. So it looks like we've had our first contact between the masses at the end of the ruler, the meter stick, and the bowling balls. So that's pretty exciting. We did see that motion toward the bowling balls then. Now there is still the question of where that equilibrium position was for the string. It didn't occur to me until just now, but when I marked the spot that it had started at and noticed that it had rotated this way, that could have been an effect of the velocity velocity that I gave it initially. It may not have been accelerating that way. Maybe it would have rotated back this way on its own. So for that, we'll have to go to the video and see if we can observe some acceleration in this direction, or whether that was just my initial velocity. But right now, it looks like a successful test and a successful replication of the Cavendish experiment. After viewing the video, I'm really happy with the results. When I went back and looked at this, after I last touched the torsion balance, this end was moving this direction, so it was rotating clockwise. But on its own, it came to a stop and started rotating back this direction. So we must be really close to the equilibrium position on this right now. So when we started it, it was over this way, to this side of the equilibrium position, and still moving this direction. When we put the bowling balls on there, it turned around, which it would have done anyway to get back to its equilibrium position, but it went way beyond where it had gone the first time. So regardless of which direction it was moving when I put the bowling balls in there, we can see there was some clear effect of the force of gravity from those bowling balls, pulling it much, much farther than it would have gone just due to its own oscillations. So again, this is a really nice example of the force from gravity between two very small objects. A good replication of the Cavendish experiment.